Welcome to another problem session. So this one is question number 3 um, from Advanced JEE from 2025. Let's see, let me get a pen here. And okay, so all right, I got it. Oh, still not writing. Oh. Okay, it's writing now. So we have paper 2, and this is question 3. So here's the figure 1, figure 2. So you right over from the figure say it's a 2 spring problem. Spring 1, spring 2, spring 1, spring 2, right? So you've seen hopefully some 2 spring problems before you come to the test. If not, this is a pretty nice place to learn it, how to handle that kind of stuff. So here is a bar. It's hinged over here. Let me get a little fatter pen. Yeah, 4. So it's hinged over here. Just look at one. This hinged over here, so the bar can actually move this way, rotate like that. Bar can just rotate that fashion, go back and forth. Okay. All right, so length is L, and then one spring is attached to that place, and another place attached to the very top. They're calling O prime, as in figure 1. So this, in this configuration, is going to have frequency F1. Okay, that's from there. Now on to figure 2. The second one being attached over there is now attached there. The springs are identical. Identical for springs, you probably already know. Is identical for springs it means this is K for this is some value K, and it's the same K, same spring constant. So we're going to use just symbol K for both of the spring constants. Okay, they don't have to be, but here they're identical. Okay, two massless springs of the same spring constant. So that's very important part of the question. And then go over there. This one is going to be this same way. It's twiddle like that, and its frequency will be F2. And you're supposed to find out the ratio of these two frequencies, F1 over F2. So we're supposed to work out F1 over F2. And answer is one of these 4 possibilities. And answer actually happens to be C, because I've solved it already. And the question is how this answer comes up. So if you can pause the video and kind of work out yourself and see how you do it and how I do it. Okay, this will be time do it. I will go on and try to solve this problem. All right. So the way I'm going to do is just do this one first and see how to set it up, and then I'll apply the same set over here. So I'm going to just assume at some point in time the bar has gone over here. Maybe just draw it out like that. Okay, this angle theta, so at some instant time is like this, arbitrary time t, and this angle is theta. So the spring has over here stretched this much, and the spring over here is that much. This has compressed, this stretched, So this bar is my system. So when what used to be say m equal mass of the bar. All right. So it's like a this is so I'm going to figure out uh, equation of motion of the bar, and this will be a rotational equation of motion. So it's going to turn out to be some moment of inertia times d squared theta dt square, or it's going to be minus some blah, that's the one we have to figure out, times theta. There will be no theta here. So from here, it's very easy to know that this is a simple harmonic motion. This would mean d squared theta dt square equals minus omega squared theta by bringing I over here. So omega square will be whatever that in box over I. Okay. What's omega is? Omega square? Omega is angular frequency. So omega is plus minus square root of box over I. And frequency is omega over 2 pi. So this will be, and frequency will be, we'll just take the positive root, 1 over 2 pi square root box over I. Now I for this guy and this guy will be same, right? So when you work out for this guy, it will use the same I because it's hinged at the same place. It's hinged at one of the ends. So if you know I, that's great. If you don't know, because ratio it will cancel out. So let's look at how this is gonna go in our case. Okay, so it's gonna be F1 over F2 will be there will be one for the case 1 and 2 for the case 2. So if you go all the way there, omega, this will be simply be omega 1 over omega 2, and when you work it out, it's going to be square root of box for the case 1 over box for the case 2. See, I just cancelled out, so I don't have no moment of inertia. I just need to figure out what this box is, okay, in each case. All right, so back to this is going to be my strategy. All right, and this is what I call it. Before, when I do the problem, I have this in my mind. It tells me where I'm going and so on and so forth. Okay. All right, so if you don't have this in mind, just randomly, I don't think you can do it. All right, just not gonna work. So here, let's look at how to write the equation of motion for case 1. And so let's call this x. This is halfway. This is L over 2, L over 2. So this whole thing is L. And so if this is x prime, from here you can do x prime equals to half x. So to get from here, you can, from similar triangles, and so this is theta, and it's approximately, you can use this divided by this is sine. So this will be equal to L sine theta, and theta is small, we'll just call it L theta. Theta is small approximation. Theta is small in radian units, okay? So meaning, remember 1 radian is around 60 degrees. So it's a much smaller. Theta small means much smaller than 1 radian. So if you have a tenth of a radian, that'll be 6 degrees. So it's going very small. So we say about 15 degrees. I can go up to 15 degrees and I'll be good enough for 2 decimal places. Good enough for 2 decimal places. 2 decimal in degrees. I mean 2 decimals in radian part. So we don't want to go beyond 15 degrees in this approximation if you want to see the same results at predicted results. Okay, so far so good, right? It's very important for you to understand these steps. So the next I'm going to do is, this is the time t. I'm going to write an equation at time t. So over here, the force is pushing that way, and there's a force pulling that way, and the gravity is that way. So this is mg, and then there will be a normal force to cancel the gravity. I mean, there's a little acceleration here in the direction. See, still forces are not cancelled here because there's acceleration in the center of mass. So there's some force here. Let's call it at the hinge. So I'm going to call it just F. There's a force there. And because I'm going to use this is an axis about which this is kind of going around, then so what are the torques from all these forces? So this is, let's call it F. I'm going to call it S is spring 1 force, and this spring 2 force, and these forces are trying to rotate this way. This is going to rotate this way. The weight is trying to rotate this way. So what will happen is let's work it out. So from here to here, that's the lever arm for S1, which is not quite L over 2, but compared to X over 2, we can use Pythagorean theorem. It will be close to L over 2. So this lever arm will be, I'll just say it's L over 2, and it's going this angle for theta is positive. This going other side, so it's going to be negative. And similarly S2 L. So these are the spring, and then we have a mg, but we're saying this angle is so small, mg is actually hitting this guy here. So this is the lever arm. Lever arm is going to be x. So mg is going to be x, and x equals to just x equal to L theta, x over to L over 2 theta, that should be equal to I d square theta dt square. So S1 and S2, what's S1 is k x over 2, that's k L over 2 theta, and S2 is kx equals to kl theta. So putting these guys in here, I will get minus k L square over 4 minus k times theta, k L square times theta, plus mg L over 2 times theta equals to the same thing on the right side. So this is minus k of 5 L square of 4. We put a minus here, minus mg L over 2 theta equals to this. So this is our box 1. So let's write it over box 1. Box 1 is 5 over 4 L square mg L over 2. Okay, so now we will work on box 2, right? So you really don't have to do extra work. You can see that this is the rod. This mg is the same. Oh, I forgot to really say that the torque by the normal about this point O, torque by normal about O is 0. So the torque by mg is the same. Then there will be this spring, now S2, let's call it prime, but S1 is same as before, and so S2 prime, this force magnitude is the same as that, so it's just gonna be like this, two of those guys. So minus S1 L over 2 minus S2 prime L over 2. This is the lever arm as before. This is a new lever arm, and the other one remains mg L over 2, and then converting these guys becomes minus k L square over 4 theta minus k L square over 4 theta plus mg L over 2 theta, and this is I d square theta over dt square. So putting this, so this thing is minus k L square over 2, these two add up, or again minus because I pulled the minus out front, minus Lg over 2 because same thing. So this is my box 2. So divided by box 2 equal to divided by k, this is k, forgot k here, k L square over 2 minus mg L over 2. Now, if you take a square root of this guy, then you have to take a square root of this whole thing. And you can see that they have made a mistake in their solution. They've ignored this. Whoever they have ignored mg L over 2 in their solution, because you can't get if you ignore that, this is square root of 5 over 2, because this will simplify to that. So otherwise you're not going to get any of the answers. If you look over there, you get none. You don't have this, you don't have this, you don't have this. This is the closest one that comes if you ignore gravity. Oh, it says ignore gravity. I kind of missed that. So sorry about that. If you ignore gravity, they didn't make. I think they just wanted to say let g equal to 0. Go to a place where g is equal to 0, outer space somewhere. So g equal to 0 place. Then it's that. Okay, then the problem answer is 5 over 2. That's correct. C is the correct answer. For a while I was thinking, where did g go? So I had to redo this problem, and only later on I realized they told us that ignore gravity. Okay, I'm glad I did without ignoring gravity, because sometimes the problem say, okay, don't ignore gravity, or don't do simplification like that. All right, so that's it for question number 3. I will do question number 4 later on. So till then, see you, bye.